Welcome dear viewers. We are continuing the discussion on transition and inner transition elements. In this module, we are focusing the chemistry of elements of the third and fourth transition series, namely the 5D and 6D series of elements. These are the 40 transition elements which are comprised of 3D series beginning from scandium, ensign, zinc, then 4D series begins from yttrium, ensign, cadmium, 5D series begins from lanthanum, ensign, mercury, and the last 6D series begins from actinium and ensign, copernicium. The third transition series. The third transition series, as you are aware, is also known as the 5D series. The name is because during the electronic arrangement, the electrons are gradually added to the 5D subshell. The elements belongs to the 5D series or third transition series are lanthanum with atomic number 57 and hafnium Z is equal to 72 to mercury. That is, it includes the elements lanthanum and other elements from hafnium to mercury. Total 10 elements. Then the general electronic configuration. The general electronic configuration of the 5D series of elements is 5D 1 to 10, 6s 1 or 2. In between lanthanum and hafnium, there occur a series of 14 elements. That element has continuously atomic number ranges from 58 to 71. These elements are called lanthanides. That is, elements coming after lanthanum has similar properties or properties more or less similar to that of lanthanum and is known as lanthanides. That is, lanthanides are the succeeders of lanthanum. And we are looking the properties of third transition series in detail. The first element lanthanum. Lanthanum appears like this. Then hafnium with atomic number 72. See, between lanthanum and hafnium there occur 14 lanthanides. The chemistry will be discussed later under the title lanthanides or inner transition elements. Moving on to the next element, that is tantalum. Its atomic number is 73 and it appears like this. This is another popular element, that is nothing but tungsten, and we all aware with the properties and use of tungsten. It is a very high melting point, made it utilize in the preparation of the filaments of our common incandescent bulbs. Then another element is rhenium. It appears like this. Its atomic number is 75, and another one osmium. Osmium is popular for its very high relative density. It is an element with very high relative density. It appears like this. Another element is iridium. Iridium is a precious metal. Then platinum. Platinum is highly useful. Its atomic number is 78 and it appears like this, and it is highly useful in the preparation of ornaments, and it is now more popular as gold. Then gold. Gold with atomic number 79 is the one of the most precious element, and we all use it for the preparation of different kind and varieties of ornaments. And the last element mercury. Regarding mercury, mercury is highly popular for its liquid state appearance at the room temperature, as well as it is highly useful in the preparation of thermometers for measuring the body temperature and the temperature of some system, etc. Now, general characteristics of the third transition series. First of all, we are focusing general characteristics such as electronic configuration, oxidation state and common properties. Then only after the completion of the third series, we can move on to the last transition series, that is the fourth transition series. Regarding electronic configuration. Regarding electronic configuration, it has been observed that the general outer electronic configuration of the 5D series of element or third transition series is 5D 1 to 10, 6s 1 or 2. Then the complete electronic configuration can be represented by this. For lanthanum, we can represent the configuration xenon core 5D1 6s2. This will be the configuration of lanthanum. Then the second element, hafnium, with atomic number 72, has the configuration xenon core, then 4 of 14, 5D, instead of 1 I have to put 2, 5D2 6s2. Like that we can represent electronic configuration of other elements also. Some elements have exceptional configuration is there, that is clear from this chart. This about the electronic configuration of the elements of the 5D series, and the two elements are shown, that is platinum and gold, has exceptional configuration because all other elements have the outer shell arrangement 6s2, but for platinum and gold the outer arrangement is 6s1. So two elements, platinum and gold, shows exceptional arrangement. Now variable oxidation state. The variable oxidation state is a very common property among D block elements. Hence, the 5D series is also not an exception. Here also variable oxidation states, as we learned in the case of the 4D series. Here also the variability of the oxidation state is maximum towards the middle. That is, for lanthanum and for mercury, the first and last element, the different oxidation states are minimum. But for the middle elements like tungsten, rhenium, osmium, iridium, etc., the maximum different oxidation states are there. Even though all the oxidation states are not equally stable, higher oxidation states have more stability over lower oxidation states. Then another characteristic feature, that is the complex formation tendency. The complex formation tendency of the 5D series is comparatively less when compared with the 3D series. This is attributed to weak electropositive nature. Since electropositivity is low, the metal is not perfectly able to receive or attract the electron pairs donated by the ligand. However, some complexes are reported till days. They include donor atoms such as halide, ligands like cyanide, ammonia, water, or pi acceptor ligands. For instance, Re2Cl8 2- is a stable compound. It is highly studied for its structure, quadrupole bonding, etc. Another example, WCN8 4-. From this it is clear that the 5D series of metals is also able to form coordination complexes. That is a general property of the D block elements. Regarding magnetism, magnetism arises due to unpaired electrons or unpaired electrons motion, that is spin motion or orbital motion, responsible for the magnetic moment. The spin component, the same equation that we used in the case of the 4D series is also adopted here. That is, spin only magnetic moment can be computed as under root n into n plus 2 Bohr magneton. Bohr magneton is the unit of the magnetic moment, and n represents the number of unpaired electrons. With increase in number of unpaired electrons, we can find out the we can see the fact that there is an increase in the magnetic moment also. See, for example, if there is one unpaired electron, the magnetic moment is nearly 1.73 Bohr magneton. If two number of electrons are there, the magnetic moment will be below 3. If 5 unpaired electrons are there, then for D5 arrangement there is a maximum of 5 unpaired electrons. Then if 5 unpaired electrons are present in the system, the magnetic moment value will be 5.91 Bohr magneton based on this equation. That is, simply put, the number of unpaired electrons in this equation, we can easily compute the magnetic moment. Then if there is contribution from orbital motion, we can't use this spin only formula. Then we have to switch over into another equation that accommodate both orbital contribution and the spin contribution. That is, the effective magnetic moment can be calculated by this equation, under root 4s into s plus 1 plus L into L plus 1. Here S is total spin angular momentum quantum number and L represents total orbital angular momentum quantum number. Then colored ions, colored ion formation, colored complex formation, that is another challenging and interesting feature of the 5D series also. In analogy with the first two series, here also colored ion formation occurs. Color mainly due to, as I mentioned earlier, color is mainly due to electronic transition. Electronic transition specifically, more specifically, the DD transition or charge transfer transition. Charge transfer transition is the transfer of electrons from either ligand to metal or from metal to ligand, simply represented as MLCT or LMCT. And the charge transfer transition is properly permitted by two important selection rules. The two important selection rules that govern electronic transition are the Laporte selection rule and the spin selection rule, and these two selection rules permit charge transfer transition, and the color due to charge transfer transition occur with very high intensity. Regarding another property, that is nothing but the catalytic activity. From the 5D series, so many industrially useful catalysts are reported. See, for instance, platinum oxide mixture is used as a catalyst under the name radiance catalyst, which is used for several oxidation reactions. So, platinum oxide catalyst is a good oxidizing catalyst. Then platinum goes catalyzes the oxidation of ammonia to nitric oxide for the manufacture of nitric acid by a process called Ostwald process. There we are converting ammonia to nitric oxide by using platinum gauze as the catalyst. Moreover, platinum black is used to prepare formaldehyde, that is HCHO or formaldehyde from methyl alcohol. This is the equation showing the oxidative conversion of methanol to formaldehyde, where we use platinum black as the catalyst. Interstitial compound formation. As all of you are aware, transition metals are blessed with so many cavities in their crystal structure, such that small elements like hydrogen, nitrogen, carbon, etc. can nicely incorporate into the cavities of the transition metal, resulted in the formation of interstitial compounds. Such interstitial compounds are stable due to the van der Waals force of attraction between the host and the guest element, and some examples are here cited. They include tantalum hydrogen 0.78. The 0.78 simply indicates non-stoichiometry. Most of the interstitial compounds are non-stoichiometric, that is, there is no clear ratio exists between the host element and the guest element, but some of them are stoichiometric also. For example, tantalum carbide, tungsten carbide, W2C, HGN, tantalum nitride, etc. etc. So, there are a number of interstitial compounds from the 5D series also. Regarding the metallic character, all the elements of the 5D series, are metallic in nature. They are most of them are hard metals, and all the elements are present in the solid state, but we are very familiar with mercury. Mercury exists as a liquid at room temperature. All other metals are solids, but mercury exists as a liquid at room temperature. Why mercury exists as a liquid at room temperature? This is because of the fact that in mercury there is very weak metallic bonding exists. As a result of the weak metallic bonding is a result of high ionization enthalpy in mercury. High ionization enthalpy in mercury is due to its very stable electronic arrangement. So, high ionization enthalpy and hence weak metallic bonding causes the liquid state existence of mercury at room temperature. So, except mercury, all are metals, almost them are hard metals, and all are solids. Then moving on to the periodic properties with respect to 5D series. The periodic properties simply means the properties of an element which can be related to the position of the element in the periodic table. There are so many periodic properties like ionization enthalpy, atomic radii, melting point, boiling point, density, so many properties. We can now look on the properties, the periodic properties of the 5D series of elements. First of all, atomic radii. Atomic radii have been found to be decrease from lanthanum to osmium. Osmium is nearly the middle element. There is not a gradual decrease. There is some increase, decrease, etc. Okay, but on a simple way we can simply talk like this: from lanthanum to osmium there is a gradual decrease, but from osmium to mercury there is a slight increase in the atomic radii is observed. This chart shows the atomic radii values specifically in picometer units, and from this it is clear that the smallest element, the smallest 5D series element, that is nothing but osmium with atomic radius equal to 126. There is a gradual decrease from lanthanum to osmium, then the atomic radius increase up to mercury. This variation is attributed to the variation in the screening or shielding effect. Melting and boiling point. The melting and boiling points of the 5D series of metals are very high except for the mercury. As I told you, mercury exists as a liquid. It is already in the molten state at room temperature. For mercury, the melting point is only minus 38.4 degree Celsius, but for other elements the melting point is very high. You just look the value of the melting point of tungsten, it is 3410 degree Celsius. That is the highest melting point for every metal, for any metal in the periodic table. That is, tungsten is highest, is having highest melting point, and that made its applicability in preparing the filaments of incandescent lamps. Then moving on to another property, that is nothing but ionization enthalpy. Ionization enthalpy deals with the amount of energy that we have to supply to remove the most loosely bound electron from an isolated gaseous atom. The ionization energy values, preferably the first ionization energy values of the 5D series of elements is shown in this chart, and from this it is clear that ionization enthalpy values, that is the first ionization enthalpy values, goes on increasing gradually as we move from left to right, that is from lanthanum to mercury. Then we have to make a comparative study between 3 series of transition metals that we learned up to this time, that is 3D series, 4D series and 5D series of elements, a simple comparison. Regarding the comparison, first of all we are taking atomic radii. Atomic radii is graphically shown here. The 3D series, 4D series and 5D series are here, and from this it is clear that the 3D series is having lowest atomic radii, but the atomic radii of the 4D series and 5D series are nearly more or less the same, and we can move on to the details. Atomic radii of 4D series are higher or larger than the 3D series. However, atomic radii of the 5D series of elements are almost same as that of 4D series. Why this happens? This happens because in between the 5D series and the 4D series there occur 14 elements, and they are lanthanides, and lanthanides exhibit a phenomena of decrease in size, that is nothing but lanthanide contraction, and this lanthanide contraction is responsible for the closeness of atomic radii of 4D and 5D series. Then abundance. The elements of the 3D series are reasonably abundant in earth or in earth crust. The 4D and 5D series of elements are less abundant than the 3D series. 3D series of elements is about 6.79% of the earth crust by weight. However, 4D and 5D elements together constitute about 0.025% of the weight of earth crust. Then coordination number in complexes. All the 3D, 4D and 5D series of elements form different coordination complexes with the high coordination number, low coordination number, etc. And we can move on the coordination number, a discussion on coordination number. The common coordination number of 3D series is 6 and 4. that is, we are familiar with the fact that the 3D series of elements form tetrahedral complex with the coordination number 4, square planar complex with the coordination number 4, octahedral complex with the coordination number 6. That is more common for 3D series. However, they generally do not form higher coordination numbers such as 7 or 8. But moving on to 4D or 5D series, we can see higher coordination numbers such as 7 and 8. They are more common compared to 6 and 4 in 3D series. Stability of oxidation states. For all the 3D series of elements, that is elements beginning from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, that series, the common oxidation state is +2 or +3, and +3 is more common state. These oxidation states are less common when we enter into 4D or 5D series. That is, for the 4D and 5D series, the stable oxidation states are higher oxidation states. Regarding metal-metal bonding. Regarding metal-metal bonding, the formation of the metal-metal bond is not favorable in 3D series because metal-metal bond formation is rare. However, the metal-metal bond formation possibility increases as we move from 3D to 4D to 5D. So, in the case of 5D elements, there is high chance for formation of metal-metal multiple bond. Metal-metal bonds. So many metal-metal bonds can present in a single compound. For instance, let us take the case of Mn2CO10. In the case of Mn2CO10, manganese is from 3D series. This Mn2CO10 consists of only one metal-metal bond. I can represent the structure here. In this structure, we can see the presence of only one metal-metal bond or manganese-manganese bond. However, moving on to the 5D series, for instance, iridium, we can see so many metal-metal or iridium-iridium bond. I am simply representing the structure of IR4CO12. It is in tetrahedral arrangement. All these are carbon monoxides. This is iridium, this is iridium, this is iridium, this is also iridium, CO, CO, CO. From this structure, it is clear that in a single molecule IR4CO12, we can see the presence of 1, 2, 3, 4, 5 and 6. 6 iridium bonds in a single molecule. That clearly indicates the fact that as we move from 3D to 4D to 5D, the formation of metal-metal bond possibility increases. Elements of the fourth transition series. We are discussing about the last transition series or 6D series or the fourth transition series. And the fourth transition series comprised of elements actinium with atomic number 89 and the elements from rutherfordium to copernicium. That is, elements from rutherfordium with atomic number Z is equal to 104 to copernicium with atomic number 112. Overall 10 elements. And the elements between actinium and rutherfordium, there are 14 elements. The element coming after actinium simply termed as actinides, and they belongs to the category of inner transition elements that we discussed later. The general electronic configuration can be 6d1 to 10, 7s1 or 2. And this chart designates the electronic configuration of all the elements of the last transition series or fourth transition series. Actinium, rutherfordium, Dobinium, Seaborgium, Borium, Hassium, Meitnerium, Darmstadtium, Röntgenium and Copernicium. These are the elements of the last transition series or the fourth transition series, and between actinium and rutherfordium there is a gap of 14 in atomic number, and they simply represents actinides as I mentioned earlier. Then the electronic configuration, there is a radon core followed by 6d 1 to 10 or 7s 1 or 2. This about the electronic arrangement of the last transition series or fourth transition series. Regarding the fourth transition series, some important peculiarities are noted. Most of them are artificial elements. That is, most of the elements of the fourth transition series are under transuranium element category. Moreover, all of them are prepared by artificial methods by nuclear experiments, and such elements exhibit radioactivity also. Moreover, most of the elements of the fourth transition series are recently discovered, and their names are also given in very recent years, and these elements from actinium to copernicium constitute the fourth series. And since most of the elements are very new elements, their properties are not explored completely. That is, we have to focus on the complete chemical as well as the physical properties of the newly discovered elements of the fourth transition series. Thus, by this discussion, we have completed the discussion on 3D series, 4D series, 5D series and the last transition series. Their general properties are evaluated and discussed. Periodic properties are analyzed or screened, and that all about the present discussion. Thank you.